Hey friends, let's go to the next problem from the homework from 6.1. That was number 13. And so I read, there's a 2-point weight stretches a spring 6 inches in equilibrium. So perhaps it's always good to have a picture. So we have, this is our y-axis. We have this spring attached here. So the y-axis is normalized so that the equilibrium is at 0. And so the spring, this is spring in its natural state on the left, and on the right is it's when the mass is attached to it, 2 pounds. So this is 2 pounds. And it stretches the spring by 6 inches. So this distance here, this is what we call the stretch. That I call the stretch. In the book they have this delta notation. It gets very confusing what they mean there, but so let's call it this way. And so an external force, so there's a force that acts as sinus 8t on this spring system, and the spring is released from rest 2 inches below equilibrium. So this is our initial condition, right? So we'll deal with that later. So find its displacement. So find the equation. Okay, so what is the equation? So our equation, because it's still undamped, is this way, right? Now, be careful. So I should perhaps point this out. I didn't do this in the previous video, but with first problem, let me write down the equation as it actually really is, right? This is how the equation is. So you have to realize that in the equation, this mass here comes from the, this is ma, this is the Newton's law, okay? So the force, when you write down this, if this is the force, if they say this is the force, then the force is part of what has to go in Newton's law, right? In Newton's law, we have the force is equal to ma. This one comes from something that we discussed before. So, but I just want to point out there is mass here. We should not forget that. So this means that our equation actually is, if you want to write it in the more standard form, is this. So we have to divide here by the mass. We should not forget that. I must admit, the first time I did this, I forgot, and that was wrong. I got the wrong. The numbers were wrong. Okay, so, well, step 1 is, of course, we need to look at a complementary homogeneous equation. And that is I'm going to focus using this one now. So that is y double prime plus km. Oh, sorry. Right, sorry. Yes. Before I do this, let's fill in what everything is now. Right now we know what everything is. Y double prime plus, what is k over m? Yeah, that's another formula that we have to keep always using, because it depends on some questions. They give us k and m. In this case, they gave us m. Well, they gave us the weight at least. So perhaps let's see. The weight was what 2 points. The weight. So the other formula is weight is equal to gm. So 2 is equal to 32m. So we see that the mass is 1/16. Okay, we'll need that. Well, you say, okay, you need it for here, but we don't know k, so we cannot use this constant. We cannot calculate using this side of the formula. We need this side of the formula because we know what s is. 6 inch, which of course is half a foot. We have to be careful that everything is put into the right measurements. So s is 1/2, g is 32. So we know that this k over m is g over s. That is 32 divided by 1/2. That is 64. Okay, so we get this equals 1 over m. Don't forget that there's a 1 over m here, which is the reciprocal of this is actually 16. So this is 16 f, and f was sine 8t. Okay, 16 sine 8t. So yeah, so this is the equation that we should look up. Not the previous one was just a general formula. Perhaps I can box this in a different way. No, let me not box that. So this is what we need. Okay, and I forgot my y here. Okay, step 1. Now I can do the complementary homogeneous. That is y double prime plus 64y equals 0. So we have the characteristic equation. is t squared plus 64 equals 0. So t squared is equal to minus 64. And so this means that t is plus or minus I radical 64, which is 8. Okay? Don't forget, this is complex numbers, right? And this means that our homogeneous solution will look like, we know what this means, right? This omega is 8. So we know that we have here cosine 8t with a general coefficient plus b sine 8t. So that's our homogeneous solution. Now, step 2. And this is where we have to be careful. Because what is the general, what we have been discussing, what should one do? What we did in the previous homework, one should take, now this angle here, so here the angle, or not the angle, I shouldn't call it the angle, the frequency. So the frequency here is 8, right? In general, this will be sine omega t or cosine omega t, or a combination of both. So the omega is 8, but this is a special case. This 8 is a, well, not 8, but 8 times I is a solution of the homogeneous equation. Okay? So what is happening here? So these are the same. So, yeah, okay, omega. They don't give, I regret a little bit that they don't give good names to this thing in the textbook. Let me see here. I guess they sometimes call this omega 0. Okay, this has a name. This is called the natural spring frequency. This is the spring frequency. Right. This is the frequency that this is the movement that a free spring that we just described, a spring that has this property, a free spring will move like this. Okay, and these are cosines and sines, so we know what that is. This goes up and down, up and down, up and down. Okay, so that is the homogeneous solution. That is a free, if there is no other force working on. And so this frequency here, because that's what the official term of a coefficient in front of t inside the cosine or sine the t is a frequency. This frequency is called the spring frequency, or the natural frequency of the spring. This force has also a frequency. And in the previous result, I have still here, we had the natural spring frequency was 1/4. Okay, the force that was, oh, there was no force applied here. Was there a force? Yes, there was a force, right? That was yes, yeah. This was sine t, so the frequency of the force was 1. They were different. Here, the frequencies are the same. Now, we should, each time that something like this happens, something special happens, both on the physical part and on the mathematical part. Let's first think about the mathematical part. What happens then? Well, look, if what we normally should do is look for a particular solution of the form, well, you take sine omega t and cosine omega t, and then put coefficients, in general coefficients. I don't need to say the same as before, because that was a homogeneous part, right? However, it doesn't matter what these coefficients are. These are solutions to the homogeneous solution, the homogeneous equation. So if you plug this into this guy here, the left-hand side will be 0, and you can never get the right-hand side. The whole point of the indeterminate coefficients is that you get something here involving a and b that you can then equate to something here. But that's not the case. We don't have that, because if we plug this in, this will be 0. So what is the rescue? What do we have to do? And I remind you what it is. The same thing happened in the case where, so I remind you that if we would have an equation like this here, a general second order equation and of the form A alpha x px, there was also a special case, namely the special case is alpha was a root, this alpha here was a root of the of this characteristic equation. Okay, because then we would normally take E alpha x, we would take this E alpha x, sorry, I said it wrong. We would take y to be u times E alpha x, that's the procedure that we should follow. But we run into a problem because alpha is already a root of this characteristic equation. What was the solution here? So if this is the case, we have to add an other power of x here. And then whatever, and then right, okay. No, I'm saying it. This is true too, but I should not point it out this way. I should say, let's. Yeah, no, it's right what I'm saying. So we would, and this is the same thing that we do here. Let me just say it this way. Just, I discussed it before, but let me just say what we need to do is put an extra t here. The variable comes in there one more time, because otherwise we will get 0 and we don't want that. Okay, so this is what we need to do. And sorry, perhaps it was a bit confusing here what I was trying to explain. What I'm trying to say is just analogous of what we need to do. Okay, so let's just do this. So y prime is then, now this is a product, so we have to take the derivative of the first, copy the second, plus 8at cosine 8t, plus, you see, sometimes I switch my sines and cosines, no big deal, right? B cosine 8t, plus the derivative of the second one, that would be a negative 8bt sine 8t, and then the double derivative, that would be 8a cosine 8t, plus now I have to take the derivative of this guy, so the first one would be just 8a cosine 8t, derivative of the second, copy the so that would be 64, and it would be a minus, right? A t sine 8t. That's the derivative of the top two terms. Now the bottom two terms, derivative of b cosine 8t, that is plus 8b minus 8b sine 8t. And then here we have to take minus the derivative of t, that is just, well, 1, so we copy all the rest. And then we take the derivative of sine as cosine, but there comes another extra 8 out, so 64bt cosine 8t. And we plug this in. So I'm going to be a little bit lazy and say, okay, this guy plus 64 times y, right? Here is our question, yeah, plus 64 times y, okay. So that was y double prime. Here this was y double prime plus 64 times y, so the 64 times a t sine 8t plus 64 bt cosine 8t, and this is equal to, that's the right hand side, 16 8at, 60 sine 8t. Now let's look at the left hand side. We're going to have, there are like terms there. So how many are there? There are actually 4 different like terms. So let me list them. The first one is, well, let's just take them as they come. 8a cosine 8t. So this is cosine 8t. What are the coefficients for cosine 8t? So that's what, no, let me just write it as coefficients. Let me write it this way, sorry. So I'm going to just write here, these are the coefficients of the term, of which term? Well, here I'm going to take cosine 8t. And this is the coefficient of the left-hand side. Okay, I could do the coefficient of the right-hand side here too, right? So, but let me not, I need more space, so let me not do this. Okay, so the coefficient on the left-hand side, coefficient on the left-hand side, for cosine t, so I'll underline them with red. That is 8a. There's another one here, plus 8a. That's a t sine t, that's a sine, that's a sine, that's a t cosine, that's not the same. There's a t sine and there's a t cosine. So these are the only two. So I get 16a. Okay? And there's nothing on the other side, so this actually has to be 0. So this tells already that a is 0. Wait, did I? I didn't forget any term, right? There should be 1, 2, 3, 4, 1, 2, 3, 4. No, I think I have everything. Okay. Let's look at the term of sine 8t. Okay, so that's we do in green. Sine 8t, we would have this one, minus 8b. Another one, minus 8b. And that's the only two signs, right? Okay, and the other side, this is 16. Okay, so we get minus 16b, so this is minus 16b is equal to 16, so we see that b is negative 1. Professor, this doesn't look good. We have already a and b, and there's still two more things to go. Let's see what happens. T cosine 8t, let's look at what's the coefficient of that. Okay, so that's a blue. Where is the t cosine 8t? There's one here, okay, minus 64b, and there's one here. Oh, plus 64b, this is 0. Good thing, because there's nothing on the right-hand side, there's also 0, so I couldn't, if it would be anything else, I would be stuck, because a and b are already determined. What about t sine 8t? Same thing, right? If the t, there's a minus 64a, and here is a plus 64a. So this is exactly what happens in the case that I was trying to describe here when alpha in E alpha x was a root of the characteristic equation where we had to adjust by an extra variable, multiply one more time with the variable. The same thing happens there. We had to, the cancellations happen, right? So things cancel. So in other words, the terms with t cosine and t sine cancel because luckily we don't have them on the right hand side. And so everything is determined. So we find that the particular solution is a was 0, so b is negative 1. So that would be minus t cosine 8t. Minus t cosine 8t. Okay, step 3. Let's put everything together now. So the general solution is the particular solution plus the general homogeneous solution. So y equals minus t cosine 8t, and then we had this now a and b. In step 2 I used a and b, but they didn't interfere with these a and b, so now I'm reusing them, right? Plus 8 cosine 8t plus b sine 8t. Okay, and so there was an initial condition. Let's read the initial condition. That was number 13, right? Which is reached from rest 2 inches below equilibrium. So the starting point, let's put this in blue here, or in red perhaps, the starting point would be here. We would read it, and it says release. That means there is no force. So we would, of course, what would happen is it would start going up first, right? The first thing will go up, trying to get, it always tries to get to its equilibrium, but it will overshoot it, most likely. We'll see, let's see. Let's see, because there's something else that's happened now. In the pre-movement, that's what happens. Okay, but in this one, perhaps things are differently. I'll discuss this in a sec. But so let's write down the initial conditions. So the initial conditions were that if t is 0, then y is negative 1, because we're below, and the velocity was 0. Okay, so plug in t equals 0. The only thing that, so minus 1, the only thing that survives is this term, so that is a. So a is negative 1. And then the derivative, okay, we have to take the derivative here. Y prime is, well, there's a product rule again, minus cosine 8t. The derivative of cosine is minus sine, so it is plus 8t sine 8t. Then the derivative of that is plus 8, no, minus 8a sine 8t. And the derivative of sine is cosine, plus 8b cosine 8t. And we put t equals to 0, we see that 0 is equal to the cosine, so this is survives, this is gone, and this survives, so this plus 8b. And so I see, right, okay, I get that 1 is equal to 8b, and so I get that b is 1 over 8. So our solution is y equals minus t cosine 8t, minus cosine 8t plus 1 over 8 sine 8t. And I just want to double check that this is what it's supposed to be. Give me a sec here, because these numbers always beat me, they always come out wrong. So since it's very easy to make mistakes like that, I'm not going to penalize you for this kind of mistakes too. Minus the cosine. Wait, they have a different a. Their a is 1/6. Why on earth is their a 1/6? Did I? B is 1/8. That is correct. But why a? that is 0, that is 0. So let's just, or was the displacement perhaps, no. I have noticed that the book makes sometimes small errors like that too. So I really don't understand why this is because if I plug in into the initial condition here for, especially this is the simpler one. So if I do this here, t is 0, well, this term is gone because of this t. This term is gone, so the only term is left is a. So a is just whatever this was, and it was -1, unless I misread that. But okay, let me see. What was the actual question? Oh, 2 inches. They got me. I swore they're not going to get me, and they get me. Because 2 inches is, of course, 1/6 of a foot, right? So this actually was 2 inches would have been, sorry, where is this? -1/6. Okay, and so this is a -1/6, and so this is why there's a -1/6 here. Okay, 2 inches, yeah. First of all, I said 1 inch. I read it wrong, and then I made a mistake of not converting inches into feet. I don't like that. I'll try to not do this. Although, of course, with inches sometimes it makes it easier to say than to write fractions. Okay. Now, one thing I want to say, although I said this is a special case from the point of view of differential equations, because we have to now consider a different type of a particular solution. Because the homogeneous solution we would normally take the homogeneous, something that looks like this, but it won't work, because we know that's the solution, the homogeneous solution. Now that is the mathematical part. What about the physical part? So what happens if we would look at this kind of the function? How would the function look like if we would graph this? And here is a kind of a sketch of this picture. So this would be my guy, and we were started here from here. So we have these two functions, this and they look a bit like a cone. So I think I should write the cone like this. And so that's and we this all these guys have the same frequency, so they all together make one kind of cyclic periodic function, but it's a periodic function that will fluctuate between these two boundaries here. And so what you see is that the movement of the spring gets worse and worse. So what is the name for this? This is what we call resonance. So this in the kind of springs is resonance. So you might have seen this a picture of these things. You've heard of this, of a bridge. A bridge is one way of modeling how bridges behave, because bridges are not really, you would think, oh, they're all metal and concrete, so they don't move at all. No, they do move. Think of a wooden bridge, for instance. But even concrete bridges have to move, because otherwise they would crack. But let's for simplicity take a wooden bridge that kind of course, vibrates, right? Now, and it has a natural frequency, the spring frequency, the natural frequency. So I said a spring frequency, but one also calls it the natural frequency of the spring. So a bridge, for instance, has a natural frequency. Now, a troop of soldiers are marching onto the bridge, and because they march in unison, it kind of puts in a force that is a periodic, right? It's like foot down, foot down, foot down, left, right, left, right, left, right, all together. So this is modeled by this kind of sine over cosine. Now, if they do this at different rates, I'll show you a picture right away, everything is okay. But if they would, the frequency at which they do their march is exactly the frequency of the marching of the bridge itself, then you get resonance. In other words, this frequency of the stamping foot is emphasizing the spring movement, the up and down movement of the natural movement of the bridge within, as it fluctuates in weather and whatnot, and of course gravity. And it makes, in other words, what it does is it amplifies the movement, and it gets worse and worse, this resonation, okay? This is what resonance is called. I mean, another thing is, for instance, yeah, okay, let me just give that as an example, okay? So, now, what happens if we do not have the force has a different frequency than the natural frequency? Well, that was the case in the previous homework. And so the picture here, oh, sorry. Well, this is the picture, okay. So the picture is, there are two frequencies now, 1 and 1/4, okay? So that means we have a bigger frequency that looks like a sine, and then with the inside, that frequency is a faster frequency, and so we get this frequency inside. So the movement goes, it starts going worse, but then it slows down, and it almost is like there's nothing happening, but then it starts vibrating again, and down, vibrate. So this is sometimes called a beat. So if you would see this on water, if you have two waves on water that come from different ways, like water that one wave is just from the, let's say, the sea waves, another wave is from a source, that like a boat, for instance, that travels through, then these waves are gonna sometimes reinforce each other, but sometimes they will kill each other. And so you get kind of this kind of strange up and down thing. It seems at some point it seems that nothing is vibrating anymore. You think, oh, it has reached its equilibrium, but no, it starts vibrating again, and even it gets worse and it gets bad again. And it actually, if there's no other force, if there is no dampening, then this will keep going, will always be the same. It will never slow down. Okay, the spring will be, the forces are such that the movement is perpetual. Of course, that's not really possible, because there is always a loss of, there is always friction, and so that we have not taken into account in our model. But if in ideal circumstances, if you would have a spring that was described in the first problem, it would start vibrating always in the same fashion, always like in a double kind of cycle. There's a shorter cycle and then a longer cycle. If you have a spring that has a natural frequency and the force that is acting upon it is the same at the same frequency, then you get something totally different. You get a reinforcement of this movement, and this movement gets worse and worse. So again, if this would go on, at the end the spring would of course crack, right? Because I mean the spring is only finite in length, so at some point this movement is no longer possible, because we are higher than the spring is attached. That's not possible, of course, yeah. But that's theoretical. So that's the difference in the physical world, and in the mathematical world, the difference is that you have a root or not of the characteristic equation. Okay, so it's kind of fun how the two things relate, right? That mathematics says, oh, this is special, and physics says, yeah, of course, this is special because.